Welcome to the lesson on differential equation and the separation of variables. This is a very common topic on the AP exam, and it's essential that you know how to solve differential equations by separating the variables. And so if you see a differential equation where you have a function of x plus a function of y times dy dx, and that's equal to 0, you can separate the variables by moving all the x's to one side and all the y's to the other side. This might sound like old news because it kind of is, but let's go ahead and find the general solution of this equation here. So if we look at this, we have x squared plus 4 dy dx equals xy. And I want to separate out the variables so that all the x's are on one side and all of the y's are on another side. So my first step is to divide both sides by x squared plus 4, and I have dy dx equals xy divided by x squared plus 4. Now I want to multiply both sides by dx, and I get dy equals xy over x squared plus 4 times dx. Now I want to divide by y on each side. I have 1 over y dy equals x over x squared plus 4 dx. And now I need to integrate. And this is going to hopefully remind you of some of the different things you need to keep in mind when you're integrating two sides of an equation. So I can't just go ahead and integrate unless I have everything I need. On the left side, it's going to be pretty straightforward. On the left side, I just have the natural log of the absolute value of y plus some constant c. Now, you don't necessarily have to write that constant c. It's going to combine with the constant c on the right side, but I'm going to do it just in case. And then on the right side, we need to do a u substitution for this to work out. Now, I'm going to let u become x squared plus 4, and then that would imply that the derivative of u would be 2x dx, which if I wanted to just do a substitution for dx, that would require that du be divided by 2x. So let's go ahead and do that now, and I'm just going to go ahead and leave the integral sign there because I haven't integrated yet. And it's going to be x divided by u, because that's what my u was, and dx turns out to be du over 2x. And then the x's will cross out from above there. You could see that this x and this x will divide to be 1. And now I have the integral of u du, which of course is just the natural log of u. And don't forget to plug that back in when we're done with this. So I just have the natural log, the absolute value of y, plus the c sub 1 equals the natural log of the absolute value of u times 1/2. That 2 from over here had to be pulled out, plus some other constant c sub 2. And then let's change back to the x's on the other side. I'm going to combine the c's first. Then I have 1/2 times the natural log of the absolute value of x squared plus 4, then plus some c3. Okay, and then you can exponentiate both sides if you'd like. I might go ahead and just take the 1/2 and move it up top first, and I'd have y equals, it's going to be the square root of x squared plus 4 times e to the c sub 3. And then e to the c sub 3 can just turn into your general c here. And I'm kind of going through and omitting some details, especially the fact that I let the absolute value of y kind of disappear when I took when I exponentiated both sides. And so that's just because that would mean that I have a plus or minus c here. I have a plus or minus solution to that, and it doesn't matter. Now what's nice about these, you can verify your solution pretty easily by just taking what you got as your answer, which is this thing down here, and what I found is basically what I should plug in for dy dx. Okay, if I multiply both sides here, and so over there, if I just plug in x squared plus 4, and instead of having the dy dx, derivative of the y with respect to x, which of course would be the derivative of c times the square root of x squared plus 4, so we have to use a chain rule. So there's going to be a c on top, but it's going to be the square root of x squared plus 4 on the bottom. And there should be an x in there. Now, what happened to the 2x? Of course, the derivative inside is 2, but when I multiply c times 2, I get another c. So I'm going to plug that in for dy dx over here. It's going to be c over x divided by square root of x squared plus 4. And then I have x on the right side, but instead of y, I'm going to put in my solution for y, which is the c times square root of x squared plus 4. And you can see now that when I divide this out, I'm going to get the same thing on both sides. This on the right side is going to be cx times the square root of x squared plus 4. And over here, this is to the first power, this is to the 1/2 power, so that's going to yield, again, square root of x squared plus 4. Okay, now let's find a particular solution. Given the initial condition that y of 0 equals 1, find the particular solution. That means once we find out what the general solution is to c, I have to plug in my initial condition that's right over here to find out what c happens to be. Now this is going to be kind of a longer one, but it is possible to separate these variables out. And so what I'm going to do first is I'm going to move all the x's to the right side if I can. So first I'm going to subtract the xy dx to the right side. Minus xy dx to the other side. E to the negative x squared times y squared minus 1 dy equals negative xy dx. Now I'm going to just go ahead and divide. And actually, technically, I'm kind of multiplying here by e to the positive x squared. And why did I do that? Because when I do that, these exponents will add together and make e to the 0 power, which is just 1. And that will effectively move over the e to the x squared to the other side. So now I have y squared minus 1 dy. And just to save time, I'm also going to do one more step. I'm going to divide the right side by y and the left side by y. Just so now I have negative x e to the x squared dx. And because multiplication is commutative, I just sort of switched around the order of these things, just so now you can see that I clearly have something with just y's in it, something with just x's in it, with their dy and dx respectively. And of course, the next step now is just to integrate both sides with respect to their variables. I'm going to do that off screen. Now you can see I have this general solution. If you make sure to follow through my integration here so you know how I got this equation. If you're just watching these and not really thinking, that's not good because you're going to be taking a test on this in just a few days. So the initial condition now is that y of 0 has to equal 1. So now whenever I put 0 in for x, my y is 1. So I'm going to have 1/2 minus the natural log of, looks like 1, which is going to be 0, equals negative 1/2. That's going to be e to the 0, so that's 1 plus c sub 3. It's easy to see now that once I solve, I get negative 1/2 plus c3. So you can see now that c sub 3 should equal 1 there. Right? And so now my particular solution that works for this problem would be that entire thing written out, y squared over 2 minus the natural log of the absolute value of y equals negative 1/2 e to the x squared plus 1. And you could leave it just like that. You can move the 1/2 e to the x squared over to the other side if you really wanted to by adding. I'm going to leave it like that. So what I've done is I've just found the particular solution given an initial condition over on the right side of the screen there. Again, make sure to work through this integration. A lot of us will take it for granted that we know how to integrate, but you'll make mistakes on the test. Example 3, let's find a particular solution curve not given even an equation. Okay, we said find the equation of the curve that passes the point 1, 3. Of course, that's an x and a y coordinate and has a slope of y over x squared at any point xy. The key part of this is just being able to read into what this is saying. Has a slope of. What does that tell us? dy dx is given to us as y over x squared. So we know that dy dx is equal to y over x squared. And just solve this using our separation of variables. You can see that I have solved the equation by using the separation of variables technique. Again, make sure you work through that yourself before you just write your summary and say I'm done. Now we have the initial condition that x is 1 and y is 3, so 3 equals c. I'm not going to use the sub 3 notation here, raised to the negative 1. Now to get rid of e to the negative 1, I need to multiply by e to the positive 1. Think about why that's going to work, because when I add the exponent, it's going to make 0. It's going to effectively make it go away. Think of this as the reciprocal of 1 over e, and I multiply by e over 1, it'll go away. So now 3e is equal to c. So that means that my actual particular solution would be 3e times e to the negative 1 over x. And you can actually combine these. They have the same base. So you could add 1 to this exponent here if you really want to and just simplify that. But there's no need for this particular problem to do that. Let's move on. We briefly talked about this, but not really deeply. But homogeneous differential equation. This is something that we're getting into some higher level stuff. Homogeneous meaning the same or being able to make separable based on a certain substitution. So you can read this. I trust that you can pause the video and read this definition and see if you understand it before I actually start working out. So I'll let you do that. So now that you had a chance to pause and read the definition, I'm going to actually work through what this definition means. So basically, if I want to know that something is a homogeneous function, what I have to do is basically use a substitution. So instead of x, I'm going to use tx, and instead of y, I'm going to use ty. And if I can pull out those t's from this after I make my substitution, then this is a homogeneous function. So let's see what f of tx comma ty is. So every time I see an x, I'll put tx. Every time I see a y, I'll put ty. So this becomes tx squared multiplied, tx quantity squared. My mistake there. This is taking the place of that x squared up there. And now this is going to become ty minus 4 times tx to the third power, taking the place of that x over here, plus 3 times tx ty it should be actually. All right, so then let's go ahead and pull out the t's where we can. So this is going to be t squared x squared ty minus 4 times t cubed x cubed plus 3t squared xy. And I think I forgot to square this thing, so it should be 3t to the third power xy squared. All right, so now what I want you to do is combine the like terms, combine the t's. You're going to get t to the third that comes out of everything. It's t to the third can come out, and now I have x squared y minus the t cubed can come out of there, which makes just 4x to the third power, plus then the t cubed can come out of that one, 3xy squared. And notice that's exactly the same as what I had up here down here. And I can just pull out the t cubed. And so we know for sure then that this is a homogeneous function, that I can make a substitution or a change of variables and be able to pull out that. So I know that this is a homogeneous, I don't know how to say that. I say homogeneous, of degree 3. And this is important because if you have two functions that are homogeneous of the same degree, you have a homogeneous differential equation. So that means that m of xy and n of xy should be able to pull out the same number of t's. And when you set that equal to 0, you should be able to solve it by using the change of variables described down here. Now this is all probably not making a whole lot of sense to you until I do the next example. But it just allows us to solve more differential equations. So for example, to find the general solution of this differential equation, x squared minus y squared dx plus 3xy dy equals 0, let's verify first that the things in front of the dx and the dy are homogeneous of the same degree. So we'll make the substitution there. We'll just plug in the tx and ty. I'm going to do that off camera. So now you can see that these two functions, the green function and the blue function, were homogeneous of degree 2 because I can pull out a t squared from both of them. So because both of the things that were in front of the dx and dy were both homogeneous, now I'll use a substitution y equals vx, and I'll be able to solve this differential equation. So let me plug in y equals vx for all of the y's in this equation quickly. So you can see now that I've used the product rule to basically take the derivative of y with respect to x. And obviously the x will turn into 1, so it's left d right plus right d left, and so dv dx had to be implicitly derived. I multiply both sides by the differential, which technically not a great way to think about differentials, but it works. I get this substitution for dy. And now you can see that everywhere I saw a y, I plugged in vx, and when I saw the dy over here, I plugged in this guy. So what you see down here is the original equation with the substitution made. Now I'm going to do some more algebra, and you'll see the solution in just a moment. And you can see that was quite a doozy of an expression. Sorry. I just didn't realize what it's going to look like from you when I pause and unpause that, and what kind of cardiac problems you're going to have. But try your best to pause at the end of this video, follow my math. all the way down here. I promise the ones in the test won't be this hard. We'll see tomorrow.